In this section, we'll take a look at the ISIS concepts objective of the JNCIS Service Provider exam. We'll examine the similarities and differences with OSPF, packet and TLV types, and designated intermediate systems. For more detailed coverage of this objective and more, please check out the JUNOS Intermediate Routing course. In this section, we're going to take a look at ISIS, or Intermediate System to Intermediate System. And in this context, when I say intermediate system, the term can be used completely interchangeably with the term router. Now, ISIS has several similarities with OSPF. We have the same distributed database that contains all the networking destinations that we want to reach within our ISIS domain. And we're populating this distributed database through the use of adjacencies running between different intermediate systems, between different routers, and over which we're sending the networking information that's populating those databases. And then on those different intermediate systems, on those different routers, we are running the SPF algorithm, the Dijkstra algorithm, to find the best path, the shortest path, to all of those destinations that are described in those databases. Now, ISIS was originally developed by the International Standards Organization, or ISO, to provide routing for their Layer 3 routing protocol called CLLS or CLLNP. This is a Layer 3 routing protocol, so it's exactly equivalent to IP. However, it never really found much deployment, and it was only really used in a few niche case scenarios, such as the routing for the control channel for distributed transmission systems. And so it was quickly adapted to also provide routing for IP. And this is the scenario that we're talking about in this video and subsequent videos. We're looking at the use of ISIS to route IP traffic. Now, ISIS, again, much like OSPF, can be deployed in a hierarchy. So this is, again, exactly the same as with OSPF. You would use if you had very many devices participating in ISIS, and some of those devices had limited control planes, so couldn't cope with supporting the distributed databases needed to describe network destinations on every single device within that ISIS domain. One of the key differences here between ISIS and OSPF is that in OSPF we have our area borders within our routers, within our ABRs. However, with ISIS, our area borders are sat between routers, and this is what I've illustrated on the right-hand side of the board here. So this is one area here, and these are separate areas, and you can see that the borders between those areas are sort of across the links that interconnect those different intermediate systems, those different routers, rather than being within the routers themselves. And with ISIS, you have this concept of level 1 and level 2. So level 1 intermediate systems will have adjacencies to other level 1 intermediate systems, and they will always be within the same area. You then have level 1 and level 2 intermediate systems. They'll maintain level 1 adjacencies to those level 1 routers that only exist within the same area. And they'll also have level 2 adjacencies, and these level 2 adjacencies span the different areas and interconnect with other level 2 intermediate systems. And level 2 intermediate systems, they can interconnect across area boundaries or within the same area, should you so wish. The level 2 intermediate systems are what forms the backbone of the hierarchy within ISIS. And as I've mentioned, so it's key to note here that we have different adjacencies for level 1 and we have different adjacencies for level 2. And these adjacencies and the flow of routing information for level 1 and level 2 are facilitated using completely different PDUs
completely different packets. Talking about the different PDUs, the different packets that support the different building blocks of ISIS, we have these different packet types outlined on the board. And let's go through these different packet types now and explore the different functionality that they provide to the overall ISIS system. So we have IIH packets, PDUs, or intermediate system to intermediate system hellos. And these are the packets that are exchanged that initially establish those adjacencies running between different intermediate systems. We then have the CSNP packets, so that's complete sequence number PDUs. These are loosely equivalent to the database descriptor packets in OSPF, and they're sent between intermediate systems, and they describe the current state of the local link state database on each of these devices. So they're periodically sent by all devices on a point-to-point link, or by the designated intermediate system on a broadcast LAN, and they're also sent on the initialization of the adjacency between these two systems. So with these packets exchanged, each neighboring intermediate system knows the current status of its neighbor's link state database. So if these link state databases are different, we then come on to the second packet type, which is the partial sequence number PDU packet, the PSNP. And this is very similar to the CSNP. However, instead of describing the entire database, it's just listing a few elements of that database. And we use the PSNP packets to request the destinations that are missing from a local copy of the link state database as we're trying to get these databases into synchronization. It's loosely equivalent to the link state request packet in OSPF. So we request the missing items from our neighbors, and then we actually populate those items using the final packet type, which is the link state PDU. And this is equivalent to the link state update packet in OSPF, and it actually contains the network destinations that's described within the database. And with these destinations exchanged between our neighboring intermediate systems, we can then bring our link state databases on these devices into synchronization. And this is a quick overview of ISIS. In subsequent videos, we'll explore some of the different elements of ISIS in a little bit more detail. In this section, we're going to take a look at ISIS TLVs. So TLV stands for type, length, value, and it's a data structure that's used to encapsulate all of the information carried within the various different PDUs, the various different packets that ISIS speaking systems advertise. Let's take a look at a TLV in a little bit more detail. So the type field contains a numeric value that's been assigned in a global registry, and this numeric value tells us the data that's going to be contained within the value portion of that TLV. It's what's giving us context to the data that's contained within the TLV. The length field is what's telling us the length, the size of the data that's contained within the value portion of that TLV. And because we know the length of the data that's coming next in the TLV, it means that it makes this data structure very easy for the computer system that's reading it to parse. And this use of TLVs within ISIS means that the protocol is highly flexible. Should we wish to add any new feature to the protocol, all we need to do is add a new TLV. So let's take a look at some example TLVs that are regularly in use with ISIS, and we'll do this using this table on the right-hand side of the board. So we have the TLV number. So this is the number that you're going to find in the type portion of the TLV. And then we have the use case to which that TLV is used for. So TLV1 contains the area address of the advertising intermediate system. TLV2 contains the intermediate system neighbour metric, so the metric to the neighbouring device. TLV6, this is used on broadcast segments, and it's the LAN ID. TLV22 is the extended IS neighbour metric, so it's TLV2 with a much larger metric field. TLV128 is a IP prefix metric TLV, so it's going to contain a root and associated metric value. And TLV130 is a external IP information TLV. So much like with OSPF, in ISIS you have the concept of internal and external routes. External routes being routes that have been redistributed into the protocol from an external routing protocol like BGP, like OSPF. And in ISIS, external routes are carried in TLV 130. TLV 132 is the IP interface address TLV. TLV 135 is the extended IP metric TLV, and it's the equivalent of the TLV 128, but again with a much larger metric field contained within it. The default maximum metric within ISIS is 63. This is because the metric field contained within TLVs 2 and 128, so IS neighbour metric and IP prefix metric, is very, very small. And obviously this very small metric means that the deployment of ISIS can be pretty inflexible. So we need to support much larger metrics within ISIS to make our configuration of ISIS much more flexible. And to support much larger metrics within ISIS, additional TLVs were added to carry those larger metric values. And these additional TLVs were 22 and 135. 22 being the extended metric version of TLV2, and 135 being the extended metric version of 128. And by default, in a standard ISIS speaking system, we're going to be advertising metrics contained within both TLVs 2 and 128, and also TLVs 22 and 135. However, by default on a typical ISIS speaking system, we're going to be preferring to use the values contained within the legacy TLVs over the values contained within the extended TLVs. So to use larger metrics, we need to suppress the legacy TLVs. And to suppress those legacy TLVs, on a Juniper device, we configure wide metrics only. And with wide metrics only configured, we can then support metrics that are 2 to the power of 24 in size. So incredibly large, and that gives us more than enough granularity that we're going to need to configure our ISIS network. And that was a quick overview of ISIS TLVs. In this section, we're going to talk about configuration within ISIS and adjacency formation within ISIS. So firstly, let's have a look at the basic configuration tasks we need to perform to enable ISIS on a given Juniper router. First thing we need to do is we need to configure protocols ISIS. The main thing we're doing here is we're specifying the interfaces that we want to enable ISIS on. We then add family ISO on these same interfaces, the interfaces we want ISIS to be speaking on. And then finally, we need to configure family ISO on the loopback interface of our device. And we also need to specify the ISO address under family ISO on that loopback interface. And this ISO address consists of 3 main portions: the most significant bits, the leftmost bits as you type them into the configuration, are the area ID. We then have the system ID. So this is the unique identifier of an intermediate system within an area. And then finally, the least significant bits, the bits on the right-hand side, are the network selector. Network selector is loosely equivalent to TCP UDP port in the IP protocol stack. And on Juniper devices speaking ISIS, this is always 00. So with this configuration in place, let's now talk about how adjacencies form on a given intermediate system. The main thing to mention here is that with level 1 adjacencies, the area ID that's contained within this ISO address must match. So the most significant bits of this ISO address has to match for two level 1 intermediate systems to form an adjacency between each other. If the area ID doesn't match, these intermediate systems do not form an adjacency with each other. So that's level 1 adjacencies in general. As with OSPF, with broadcast segments potentially containing many separate routers, we do have a way to summarize the routing information regarding that broadcast segment so that we're making the distribution of this routing information within the intermediate system domain more efficient. Within ISIS, we have a designated intermediate system, much like the designated router within ISIS, much like the designated router within OSPF. When we have multiple routers, multiple intermediate systems interconnected to a broadcast segment, the first thing that happens is we go through a DIS election process to decide which of the routers connected to that broadcast segment should be elected as the DIS. And with DIS election, the highest priority wins. We have a priority value of 0 to 127 possible, with the default being 64. If priority values are equal, we then tie break on the MAC address of the speaking IS on that broadcast segment, or the SNPA, the subnetwork point of attachment address of those intermediate systems. And unlike the OSPF DR election process, the ISIS DIS election process is deterministic. So say in this example, drawn up on the right-hand side of the board here, we initially only had these two routers present on the broadcast segment, and this router had been elected the DIS by virtue of having a higher priority than this router here. Now say in the future, this router interconnects to this broadcast segment, and he has a higher priority than the current DIS. He is then going to preempt this DIS and become elected as the DIS for the whole segment. And this is different to the way that OSPF elects a designated router. And another difference with OSPF is that we don't have a backup DIS. We have no equivalent of a BDR. Another difference with OSPF is that we still form neighbor adjacencies between all devices that are interconnected to the same broadcast segment. In OSPF, we're only forming adjacencies to the DR and the BDR. In ISIS, we form adjacencies to the DIS, but we also still form adjacencies between each other. The summarization of information flow comes because what we're doing is we represent the connectivity of all the devices interconnected to the same broadcast segment as if they're belonging to a virtual router. This virtual router is named the pseudonode, and this represents all of the connectivity on the broadcast segment. And it's only the designated intermediate system, the DIS, that advertises this pseudonode connectivity to the outside world. This is what gives us the summarization of information within the broadcast topology, which gives us similar functionality to the DR and BDR within OSPF. This was a quick overview of some of the likely configuration tasks you'll need to perform with ISIS and how adjacencies are formed within ISIS.